Hello and welcome to the course. This is actually the first part of the Quantum Mechanics course series. Quantum Mechanics 1, or also called Physics 123, will tackle about the basic postulates of quantum mechanics, while the next course, Physics 124, will tackle about more advanced topics. For today, we will have an introduction to the basic concepts of quantum mechanics. As you can see in this figure here, these are atomic orbitals. You have encountered this in your basic chemistry courses, and we will relate quantum mechanics to that. Let's first go back to the different realms of mechanics. We can actually categorize the realms of mechanics depending on the size of our particles and the speed of which they are moving. So their sizes can be relatively large, relative of course to an atom. So if you have an atom, that's actually relatively small. You have electrons, protons, neutrons. Those are relatively small particles. In terms of speed, we measure it relative to the speed of light. So if you are moving very slow relative or compared to the speed of light, then we say that you are relatively slow. And if you are moving near the speed of light, then you are relatively fast. So for particles moving for relatively large particles moving at slow speeds, that's actually the realm of classical mechanics. So you have taken uh, courses on classical mechanics, Physics 21, University Physics 1, and also your classical mechanics 1 and classical mechanics 2. So the objects of interest here are relatively large and relatively slow objects. When the relatively large objects, are moving at fast speeds near the speed of light, then you will, or that's the realm of relativistic mechanics. You actually have encountered or studied this realm when you took modern physics. So you studied the special theory of relativity of Einstein. Now, if you have relatively small objects such as photons or electrons, and they're moving uh, very slow as compared to the speed of light, then that is the realm of quantum mechanics, and that is our what is our that is our course, quantum mechanics. And if you are dealing with relatively small objects moving at very fast speeds near the speed of light, then that's what we call that's the realm called relativistic quantum mechanics. So when you're dealing with gravitational waves, so here that it's in this realm. But for our course, we'll only focus on the realm of small and slow particles, and that is quantum mechanics. So before we proceed, I will just point out what are the things that you need for this course. So since the prerequisite for this course is modern physics, so you need to know or review this concept. So Planck's radiation law, so black body radiation, Einstein-Levy theory of specific heat. So temperature is just due to vibration of molecules. The Bohr atom, the most accepted model of the atom. De Broglie's matter waves, in which matter can behave as waves according to the theory of de Broglie. Then Compton effect, so it's called, or some also call this Compton scattering. Uh, Related to Compton effect is photoelectric effect. The Frank Hertz experiment, Davison-Germer-Thomson experiment, which confirms de Broglie's matter waves, and the Stern-Gerlach experiment, which confirms the quantization of uh, spin angular momentum of electrons. So take note, quantum mechanics comes, the word quantum in quantum mechanics comes from the word quanta. So when you say quanta, there is quantization. For instance, our currency, the peso, is quantized in multiples of 5 centavos, meaning you cannot see, or you cannot produce 6 centavos, you cannot produce 7 centavos, but only a multiple of 5 centavos. So that's what we mean by quantization. So in the Stern-Gerlach experiment, they have found out that the angular momentum is a multiple of the Planck's constant, and not an integer multiple of the Planck's constant. And you cannot find spin angular momentums which are not multiples of the Planck's constant. So most scientists or physicists attribute the formulation of quantum mechanics to these big three names: Heisenberg, Schrödinger, and Dirac. So actually we will encounter these three names over and over in our course. So quantum mechanics has two basic postulates, and those are the wave functions and the operators. The wave functions represent the state of the particle. It describes the status of the particle in the same manner as position, velocity, momentum, or acceleration describes the state of a classical particle. Operators are just physical observables. So your momentum, your position, those are physical observables, and they are represented by operators. And one of the most important equations in quantum mechanics is the Schrödinger equation. So this is actually a wave equation where psi here is what we call our wave function, and it's a function of position and time. But actually you can also have wave functions which are functions of momentum and time. So you have already derived this in your modern physics, starting from the generic form of a wave, the mathematical description of a wave, and then you use the quantum mechanical results. So you actually started with the mathematical description of a wave. So the wave has an amplitude, and a wave can be represented by a sinusoidal quantity. And what best to represent a sinusoidal quantity than an exponential function, e to the I theta. So this is the physics 31. When you discuss about waves, this is the physics 31 mathematical description of a wave. K here is what we call the wave number, omega here is what we call the angular frequency. So you incorporate the quantum mechanical result, so such as the de Broglie wavelength, which is just equal to the Planck's constant over the momentum. Take note, wavelength lambda is a property of a wave. Momentum p is a property of a particle with mass m and velocity v. So this is actually a very important equation because it represents the wave-particle duality of everything, not just matter. So wave is related to a particle and a property. So we will also use the result by Einstein when he described the photoelectric effect, that a single photon has an energy of h times f. H is the Planck's constant, f is the frequency. So we will use this quantum mechanical results and then substitute it back to our mathematical description of a wave uh, in order to derive our Schrödinger equation. And we'll also use the total energy operator, which is just kinetic energy, 1 half mv squared, or in terms of momentum, p squared over 2m, plus the potential energy. So this is the energy operator. And we will let the energy operator act on psi. And using the quantum mechanics results and the total energy operator, we can derive the Schrödinger equation. So actually, I'm sure you have already done this. Okay. So the Schrödinger equation is analogous to Newton's second law of motion. It's actually an equation of state, a state equation. So you will notice that psi here, our wave function, is a solution of the Schrödinger equation. So the same in classical mechanics, usually you are given an initial value. So in this case, if you are given the initial wave function, the wave function at the start at time is equal to 0, then the Schrödinger equation can give us the wave function at any time t. So in the same manner, when in classical mechanics, when you are given the initial position or initial velocity, you can find the final position and final velocity of the object at any given time t. So the Schrödinger equation is similar in that matter. So as a comparison, there are many state variables in classical mechanics. So one is position. Its analog in quantum mechanics is the position space na wave function. So the wave function is a function of x and t. Another analogy is if you have the time-dependent momentum in classical mechanics, its quantum mechanical analog is the momentum space wave function. So those are the comparisons. So in general, the wave function represents the state of a quantum particle. Note that we are in the quantum world here. We are dealing with very small objects. So we cannot use the wave function to describe classical particles. So according to Max Born, the wave function can be statistically interpreted as related to probability. So according to Born, if you integrate the absolute value of psi squared over a measure, say dx, then this will give you the probability that a particle's position at a certain time t is between A and B. Or in other words, this gives you the probability of finding a particle between A and B. What's the chance that the particle is between A and B? The integrand here, the absolute value of our wave function squared, is what we call the probability density. In this case, this is probability per unit length. But if you have two dimensions, it becomes probability per unit area. Or in 3 dimensions, it's probability per unit volume. So if you plot the probability density as a function of say position, say in 3-dimensional position, you will actually get the atomic orbitals. So in chemistry, atomic orbitals are just the 3-dimensional plot of the wave functions. So we have here the s orbital, spherical, the p orbital, px, py, pz, and the d orbital, d orbitals. So this is just a probability density plot. Sometimes we call it a probability cloud, meaning in this cloud, there are, in the s orbital, for instance, there are two electrons that can occupy this probability cloud. In the case of the p's, there is two electrons in each of the p components, px, py, and pz, and you have a total of 6 electrons that can occupy in the p orbital. So if you actually plot psi squared as a function of x, you get a density plot and you get the atomic orbitals. You can also have the momentum space wave function. So if you integrate the momentum space wave function, phi squared, over momentum, dp, then that will give you the probability of finding the momentum of the particle. So in this case, you get the probability that the particle's momentum at a certain time t is between a and b. And for this case, the probability density is probability per unit momentum. So a typical wave function plot, the absolute value of psi squared plot over versus x can be like this. It's actually a wavy. It's a wave. So based on Max Born's statistical interpretation, the integral of psi squared from a to b is just the area under this curve. So take note that the y-axis here is psi squared, probability density, probability per unit length, and the x-axis is x, which is a position or length. So area is just y times x. So probability density times x, and that will give you probability. So probability per unit length times length is probability. So the area under the curve here represents the probability of finding the particle between A and B. In this case, you will notice that there's a peak here, say at point C, and this has the highest value of probability density. So this will also give you the most probable value. In this case, the value that we're talking about is the position of the particle. So the most probable position of the particle will be at point C. So if you are asked where's the particle most likely to be if its wave function is given as this one, so then your answer should be C, because that has the highest psi squared or probability density, meaning it also will have the highest probability. But take note that based on the Schrödinger equation, the wave function evolves with time, meaning at a certain time, the shape of the wave function or the curves of the wave function will change, meaning the probability between A and B may also change. So in general, probability is actually time dependent. Depending on what time is it, the probability is different from a certain or from a previous time. But there are also special cases wherein the probability is time independent, and that is what we will focus on this chapter. So if you'll also notice here, the point C is no longer the highest probable or the most probable value. In fact, it's now point D. So the question now is, when you measure the position of the quantum particle, where was the particle before you made the measurement? So this is actually a very mind-boggling and tricky question. So there's two schools of thought or interpretation for the answer of this question. There's the Einstein interpretation, which Einstein states that the position of the particle was merely unknown to the experimenter. but the particle's position is determined. Say, the particle is actually really there, but the experimenter, the one who measures the position, just doesn't know it yet. The second interpretation is the Copenhagen interpretation, which is also the quantum mechanics interpretation. By the way, Einstein is not a fan of quantum mechanics. If you remember, or if you maybe have read some of his quotes, one of his quotes is, "God does not play dice." But quantum mechanics is just like playing dice. You can't determine. There's no, you can't determine the outcomes, just like in classical mechanics. So all you can get actually in quantum mechanics is the probability. You don't know uh, you cannot determine, you cannot predict. There's no such thing in quantum mechanics. There's no such thing as destiny. There's no determinate values. So in the quantum mechanics or Copenhagen interpretation, the position of particles is indeterminate, meaning the particle wasn't really anywhere. It's not, its position is not determinate, and it's uh, it's intuitive because this is not the quantum world, and we, the experimenter, are classical beings. So there's a limitation to what we can determine. So in this interpretation, the act of measurement itself forces the particle to take a stand. So initially the particle is not anywhere, but when you measure the position of the particle, you're actually something like trapping. You're actually confining or trapping the particle, forcing the particle in one location. So this further means that the observations or measurements actually disturb the wave function, and in turn they produce the measurement. So most experiments verify the Copenhagen interpretation. So the Einstein interpretation is actually not the correct way to answer this problem. So for instance, you have this wave function before you measure the position of the particle, but upon measurement, you're actually collapsing the wave function. So the wave function collapse wherein it peaks at a certain position value, say in this example, x naught. So the moment the act of measurement forces the particle to take a stand. So that one. And which means if you no longer observe the particle, the wave function will relax again. It will relax again. And if you measure it again later, then you again forces the particle to take a stand, and you will expect that you will get a different result. So that's the weird thing about quantum mechanics. Every time you make a measurement, you get a different result. So every result only has a certain probability that you will get that answer. But if you measure the position quickly after your first measurement, then the wave function has not yet relaxed, then you can still get the same value. That is if you make a quick measurement. So that one. So the wave function will collapse if you make a measurement. So in quantum mechanics, you will only get probabilities. The probability that the particle is in this position, the probability that the particle is in this position. There will be positions with higher probabilities. There will be positions where it is very unlikely. We can also use the momentum space wave function if you want to measure the momentum of the particle. So that's the end of this lesson. So for the next topic, we will be discussing about some basics of probability and how to calculate probability given a probability density function. So see you next meeting, and thank you for listening.